Suppose omega f fn p be a filtered probability space and xn be an adapted process in it. Now define yn as a sum of this xi, I from 0 to n, so that this yn is a martingale. So now it is like converse of the opposite problem of the previous problem. In this time you have given that this yn is a martingale already. Now we have to prove that conditional expectation of xn plus 1 given fn is 0, and in general conditional expectation of xn given fm is also 0 for all n greater than m and m greater than or equal to 0. Next we have to show that expectation of xn is 0 for all n greater than or equal to 1, and next we have to show expectation of xn multiplied by xm is also equal to 0 for all n greater than m greater or equal to 0. So if you have understood the previous problem solution, then this is the converse of that problem actually. So when and here in this problem we have not assumed that the random variables are independent. So in this problem it is given that if this summation of random variables forms a martingale, then we are going to get the following informations of these random variables, that is the conditional expectations as 0, and in general any this m. So it is not the fact that a conditional expectation of the next given the sigma algebra up to previous one is 0. In general conditional expectation of xn is 0 given the sigma algebra behind the n minus m also. So and here condition expectation of product of any two random variable given that with this relation is also 0. Now since yn is in martingale, This means conditional expectation of yn plus 1 given fn is yn for all n greater or equal to 0, right? So this means conditional expectation. Now what is yn plus 1? Yn plus 1 can be written as yn plus xn plus 1, right? Given fn is equal to yn. Now this can be further broken as fn. This can be further broken as conditional expectation of xn given fn is equal to yn. Now since yn is fn measurable, so from the property of conditional expectation we can write this fn is equal to yn. So yn and yn get cancel out, so conditional expectation of xn plus 1 given fn is 0. So the partial of the first part of this problem is solved. Now we will see that in general conditional expectation of xn given fm is 0. Now we will show that conditional expectation of xn for any fm is equal to 0 for all n greater than m greater or equal to 0. Now we will use this property for any random variable z expectation of z can be written as expectation of conditional expectation of z given some sigma sub sigma algebra G, given the fact that G is contained in F1, and also for any random variable z, conditional expectation of z given some subsigma algebra H is conditional expectation of z given z given H. This is something called Tower law of expectation. Okay, let us see out of two equality which one we should use. Now conditional expectation of xn given fm can be written as conditional expectation of xn given fn minus 1 given fm, right? Now this fact, this you can take H, you can think of H is fm, which is contained in G, which is can be thought of fn minus 1, and we have given n greater than m, right? Now look at this term inside. Now since xn is independent of fn minus 1, and we have proved already in the previous uh, part of this problem that conditional expectation of a xn plus 1 given fn is 0. So this is 0, right? So instead of n you just put n minus 1 here. So that means finally we are going to get here actually conditional expectation of 0 given fm, which is 0. So we used actually this tower law property. This is called tower law property of expectation, conditional expectation. Now in the second part we have to show expected value of xn is equal to 0 for all n greater than equal to 1. Now since yn is a martingale, this means expected value of yn is constant, right? So say some k. Now this means expected value of yn plus 1, which can be written as expected value of yn plus xn plus 1. This is also equal to constant. So this means expected value of yn plus expected value of xn plus 1, which is equal to k. Now so this is constant. Expected value of xn plus 1 is k. So expected value of xn plus 1 is equal to 0. So this means for all n greater than equal to 0, so expected value of xn is equal to 0 for all n greater than equal to 1. Then the last part of this problem, we have to prove that expectation of xn into xm is equal to 0 for all n greater equal to m, sorry, greater than m greater equal to 0. Now we use the fact expectation of any random variable z is conditional expectation of conditional expectation of z given some sigma algebra z, right? And we proved on fact that conditional expectation of xn given any fm is equal to 0, right? In the first part of the problem we prove for all n greater than m. Now choose zn is equal to xn product xn. Now if you use this fact, conditional expectation of xn xm, sorry, expectation of xn xm, so this is our z, this is expectation of conditional expectation of xn xm given fm, right? Now xm is fm measurable, so we can take that part out, xm, and then conditional expectation of xn given fm, but this quantity is 0, so we can write 0, and then this is 0.